So this is the last lecture of the 4 lectures. To begin with, let's start with something very light, and then we will return to where we were last time. So we will look at a little lemma that will hopefully help you clarify what was going on. So consider V to be a k-1 dimensional subspace of Rn. So when we define the k-broad norm, k-broad LP norm, we consider this the sets of tau such that the angle of g tau, so we call that g tau is here and g tau is the normal direction on the paraboloid. We will consider the set of tau such that the angle between g tau and the subspace V is bounded by 1 over k, where k is a large number. So this little geometric lemma tells us that this set lies inside the 1 over k neighborhood of k-2 plane W in Rn-1. So this is our tau, and the claim is that we can find a little W that contains that is 1 over k neighborhood contains all the tau that we are interested in. So the proof is simple. So let's C tau be the center of tau, and then G tau can be parameterized by this vector. So we just calculate the normal vector at C tau on the paraboloid. And suppose that V is parameterized by those linear equations, then we can define W to be the set of C such that the corresponding normal vector dot product with those AJ vectors used to define V to be 0. And this will be k-2 plane W in Rn-1. So this is just a simple geometric calculation that's whenever we discuss some condition like this, what we should really have in mind is a k-2 plane in the n-1 dimensional space, and then the tau lies within it. In particular, the set of tau, if we pull back, it will lie in the 1 over k neighborhood of a lower dimensional paraboloid. Okay, so this was like an independent lemma, but I hope it will help you understand what's going on later. Okay. Now let's go back to where we ended last time. So maybe this page. So last time we did the polynomial partitioning. We find a polynomial, and then we define its neighborhood as W, and then the complement of W is decomposed into union of cells. The number of cells is D cubed, where D is a large constant only depending on epsilon. And then each cell is contained in a smaller ball of radius R over D. And we have decomposed into algebraic case. So that's when the neighborhood of the algebra variety dominates. And then for the algebraic case, we have decomposed into a tangential case, the tangential part and the transversal part. So the tangential part are defined as the what the set of tangential wave packets contribute. And the tangential wave packet will satisfy that, first of all, it should roughly lies inside the neighborhood. And then it satisfies some angle condition with respect to the tangent plane. And we have seen in the second lecture that this angle condition was used to show that if a tube is not tangential, then it is transversal and it does not intersect the algebraic variety into too many times. And okay, now let's focus on the tangential case. So to estimate the tangential case, so here, as we have seen earlier, we can decompose the W, the set. So S is W intersect a slightly smaller ball. We can decompose our set into union of cubes of side length r to the 1/2. And then by the by the tangential tube condition, for example, all the tubes that intersecting this cube, by our tangential condition, it should lie inside the this r to the 1/2 neighborhood of the tangent plane. At z, where z is any point inside z is any point inside q intersect z. So this whole fat red plane, red slab is the r to the 1/2 neighborhood of the tangent plane, and this is by our tangential tube assumption. And then by the lemma that we have seen at the beginning of today, it tells us that the corresponding direction, that's the thetas, so those tubes are t theta. Those corresponding theta will lie in, on the paraboloid, it will lie in the r to the -1 neighborhood of a parabola. So what I wanted to say here is that when we consider the tangential case, we really reduce the dimension. So here is how we can see that we have reduced the dimension. And so the set of tubes intersecting Q in the set of tangential tubes intersecting Q will look like a two-dimensional problem. And also, this is like the bilinear. So here we are considering two broad norm. So it's like we are estimating a bilinear bound. So here we consider this bilinear L4. So 2 + 2 is 4. Bilinear L4 bound on Q. And then here now we can apply the argument in R2. So if we have two caps, tau 1 and tau 2, they are transversal. And also, when we look into what caps will contribute to this function, it will lie inside this r to the -1 neighborhood of a line, of a parabola. Then, so now this is reduced to a two-dimensional problem. Now we have the Cordoba argument, saying that for any theta j in tau j, where j equals to 1 and 2, and the distance between tau 1 and tau 2 is like larger than 1/k, which is like a constant compared to r, then theta 1 and plus theta 2 will not equal to, so for most of the pairs, theta 1 and theta 2, their sums will not be equal to each other until the pair is the same pair, unless the pair is the same pair. So the theta j's are the r to the -1/2 caps. And now this inequality is a consequence of this geometric this Cordoba type argument. Now, so this is done by expanding those sums, and then we only have the diagonal term, and the non-diagonal term will have zero Fourier support, and because of this. Okay. Now, so this inequality is from last page. From the Cordoba type argument, we have this. We have split into sum over wave packets. Now here, recall that in R3, EF theta V is like a certain weighted tube. So it's like a constant on its essential support, T theta V. Now we replace this approximation on the last line. And also previously we have one single Q. Now we sum over the Q lies in S. And then here we apply another geometric observation. That is, if the distance between theta 1 and theta 2 is larger than, so this is 1 over K. And now, which means that the angle between T theta 1 V1 and T theta 2 V2 is like larger than R to the minus epsilon. So when we integrate on S, it's like we have two tubes. They only intersect in a small cube. So this integration is bounded by the volume of the cube. And we plug in, and then by the L2 orthogonality that we have seen earlier. We have the last inequality. So those calculations are like what we are. So those calculations are like standard for a restriction type problem in R2. So I just want to review it and then have a sense of how we use the properties of wave packets and how do we use the bilinear assumption, the transversality. From the previous calculation, we obtained an BL4 bound on the tangential part. And we also have the L2 bound. That's the energy estimate. Then we apply Hausdorff's inequality and to obtain the final inequality for the P that we are interested in. So the previous calculation can be replaced by if we also do Hausdorff's inequality using Tau's bilinear restriction estimate. That is, so he shows that the bilinear version of, in this case, we can also say that BL 10 over 3, BR is bounded by F, L2 norm of F. So this is the theorem of Tau in R3. But this theorem is like stronger, so it works for all functions with Fourier transform supported on the paraboloid in R3. What I was trying to say is that in the tangential case, we have reduced to a problem in R2, so we can apply those easy techniques in R2 to obtain this bound. And now we have obtained a restriction inequality for the tangential part. And here, this is the power of R we get. The precise exponent is not very important, but you see when P equals to 10 over 3, this is 0. So this is like having this has the same strength as if we apply Tao's bilinear restriction theorem here. But so now we are interested in the P equals to 3.25 that is smaller than this exponent. When the smaller P is the larger, the better estimate we get, then this quantity will be way larger than 1. So we need something to, so this is like kind of like the loss we have, but we also need something that help us. So this is where we apply the geometric theorem. So, so previously, when we think about polynomial partitioning, there are 2 key properties. One is that the number of tangential tubes is not too large. And the second one is that if a tube is transversal, it does not intersect to the algebraic variety many times, and also the tubes does not intersect the cells many times. So this is the geometric theorem saying that there won't be too many tangential tubes. The theorem says that the number of tubes pointing in separated directions contained in the neighborhood, whether the size of a neighborhood of an m-dimensional algebraic variety Z is less than some power. And so how to remember this quantity? Usually when I remember those things, I will think this is the quantity number when Z is M plane. Maybe I will say approximately the number. So one tricky part when we apply polynomial partitioning is that we have to deal with neighborhood of the polynomial. But this geometric theorem says that in some sense, we can view this neighborhood as if it was flat. Now, this theorem in when n equals to 3, Guth used the Hellbrush argument. But when n is greater than 3, this is very non-trivial, and they used deep results in semi-algebraic geometry. This was done by Katz and Rogers. And one key ingredient is the Bonque's lemma that we have seen in the second lecture. But we need to know more about it. Now, as a corollary, since the number of directions for tangential tubes is like small, it's like lower dimensional, then we have, when we pass from L2 to approximation of the L infinity bound, we have some gain. The reason is that here, what this geometric theorem says is roughly the number of theta is like in a lower dimensional plane. And then, for example, this is the unit disk in Rm-1. So that's why it has smaller support. And then when we pass from L2 to L infinity, we have this gain. And this BLP bound was what we obtained earlier. So sorry, there is a question. Itama asked, Cordoba-Tao's bilinear theorems seems to play a crucial role here. If one takes the k-linear versions of their theorems, can they be used in this context? or does it have to be the bilinear one? That's a great question. So this is related to the question Lillian asks at beginning, like what's the value of K? If we are working on, so all those BLP here is like too broad. So if we are working on EF as tangential, not even tangential, I think any function, if we are working on BLK. So here if we have some K linear bound, indeed we can apply. That will be helpful. But the problem is that we don't have a K linear bound, and except from when K equals to n, that's the multilinear estimate done by Tony here, and Capri and Bennett, Capri and Tell. And now, so as you will see, maybe later today, we can actually use the polynomial partitioning to prove a K-broad bound. In other words, if we know how to do polynomial partition in higher dimensions, we can avoid using Cordoba and bilinear theorem. That will be the another technique that's in a higher dimension. Oh, there is. Sorry, I don't know. There is a recent K-linear bound by Bajunaro. I was not aware of this paper. I will take a look at. Thank you for pointing out. So let's continue. So here is this restriction estimate in passing from BL too broad BLP bound, BLP as norm to the L2 norm, and then if we pass the L2 norm to the approximation of an L infinity norm here, then we have some gain. So this is the loss and this is the gain. So we have to balance things. For example, one thing is that if we are in the tangential case at the beginning, then if we plug in, then we will see that as long as P is greater than 5/2, we win. But that's very fortunate, and usually we won't be able to attain tangential case at the beginning. Okay, maybe I will pause and see if there are questions, more questions. Okay. So that was the tangential case. And now for the transversal case and cellular case, things are like as before. Recall that S is this neighborhood of the algebraic variety intersecting a ball of radius r to the 1 minus delta, and delta is a very small positive number. And then, so this is what, when we say we are in the transversal case, we mean that the BLP norm of EF on BR is bounded by summing over the transversal part. And also by the geometric lemma that we proved in the second lecture, each transversal tube intersects this W into d to the some constant times n, maybe just d to the n. It will contribute to d to the n many balls, B row. So each tube T belongs to at most, I think, this many set TS transversal. And that was the geometric lemma we proved. So as a corollary, when we sum things up, we overcount this many times. So that's the information we get from the transversal case. And since the radius, since S lies in a ball of smaller radius, so we can apply. We are in a place where we can continue applying polynomial partitioning. Now, for the cellular case, we define the function fo as summing over the wave packets intersecting our cell O. Then this is the definition of the cellular case. So if the BLP norm of EF is bounded, I think I missed the P here, is if the BLP norm of EF is bounded by D cube times times the BLP norm on a cell for a typical cell in this many cells. So this was this is a result from the polynomial partitioning. And then we are in the cellular case. And the polynomial partitioning tells us that if we are not in the tangential case or transversal case, then we are in a cellular case. And in particular, it says that each single cell is less than average. But if it's also bounded below by this function, then we know that for a typical cell, it should be roughly the same. Maybe I will add roughly the same. Okay, and this follows from the fact that each tube intersect at most D many cells. So those are the two information we get from the transversal case and cellular case. Now we take a minute to look at what happens. So first of all, here, the radius of the ball is like relatively small compared to R, in the sense that now D is a large constant depending only on epsilon, but the size of rho is like R to the delta fraction smaller than the previous R. So now D is way smaller than R to the delta. And so all the things that happen on this page tell us the following story, is that we have decomposed the space into many parts, where this many either means the set of S or that it means D cube. And each tube do not interact with each tube interact with only few of them, where this few means either D to the N or D in this context. So those two cases now looks very similar in spirit, and we are going to treat them in the same way. So now things looks kind of similar to the toy problem. So we first apply polynomial partitioning, and if we are in the tangential case, as we have just discussed, we are in a very good position. As long as P is greater than 5 halves, we win. So we can assume that we are not in tangential case. And now assume that we are in the cellular case or transversal case. In either cases, we will continue polynomial partitioning. And so now we continue partitioning. And each step, we make the radius of the ball smaller. And assume that we have, we will only stop when the radius is smaller than R to the delta. Or we stop when we are in the tangential case. because we know how to do our estimates in the tangential case. So that's like two stopping condition, either tangential case or the radius is too small that we can apply some trivial estimate. So we first discuss what happens when the radius is too small. And this will look like the wishful thinking step in the second lecture. So things become pretty good. So when the radius is smaller than r to delta, suppose that we have done m steps of cellular cases and l steps of transversal cases. So the number of steps is not given by us, it's given by the function. So we don't have control of them. All we know is that the radius is smaller than r to the delta. And combining the estimates in the previous page, since we have applied m steps of cellular case, then we know that EFO, where O is the so where this O is either this S or this O in the last step. And we know that those part, it has a small, so we know that the BLP norm of EFO is d to the minus 3m fraction of the BLP norm of EF on BR. Then we also know that how the wave packets overlap. So we have this L2 bound. This follows from the d to the m because we have m steps of cellular cases, and each step we lose a power of d, and this is because d to the 3l is because we have l steps of transversal cases. So here, recall that when we are in the transversal case, the radius will go from r to the 1 minus delta. This means that the number of transversal steps will be smaller than some constant only depending on delta. So this is like a very small number. And as a result, so this d to the 3l, the 3 is not important. It's okay if you put 30 here. So this number is a large constant only depending on epsilon and delta. So d equals to d epsilon. So that means that this is something we can just ignore, because it's bounded by r to the epsilon. But this m could be huge. So those things we cannot ignore. And then by our assumption that we stop at radius r to the delta, we have this inequality. And here we can apply a pigeonholing step. So we sort the size of this quantity and then we find a popular quantity. So this number of O is the popular O. So it's the O such that the EFO, the BLP norm of EFO is the popular quantity. So this is done by applying a pigeonholing step. But since we have this estimate, it implies that the number of O should be larger than d to the 3m. And since each O lies inside a ball of very small radius, we can apply some trivial estimate. So we can lose some power of the radius. For example, those trivial estimate can just be LPO smaller than the diameter of O to the, say, 3 here times FO L2 norm. Those estimate is easy as long as we are willing to lose some power of the diameter. And again, here, since the number of cells or those S in the transversal step is larger than d to the 3m, then by property B, for a typical cell that we are considered in this number of quantity, it should have small L2 norm. And if we put things together, the BLP norm of EF is bounded by the L2 norm of F as long as P is greater than 3, under the condition that all this polynomial partitioning will stop at this radius. Okay, I will pause and see if there are any questions.
Wang, so roughly speaking, the reason that M can be really large but L not so much is because you gain, the change in R is so much bigger in the transversal case?
So the reason is that in the transversal case, we have reduced our radius from R to R to the 1 minus delta. That's a lot.
Mm-hmm.
But in the cellular case, we reduce the radius by a factor of d, where d is just the constant depending on epsilon.
Okay, very interesting.
Thank you for your question, Olivia. So if there are no further questions, let me go to the interesting step. That is, what happens when the tangential case is dominant? So now suppose that after m steps of cellular cases and L steps of transversal cases, so those m and L, they can happen one and another, they can happen in all different orders. And then we arrive at the tangential case. Now imagine, so those functions are tangential to a fat surface S inside a ball of radius R, where we don't have any control on this radius R. It just happens with the function itself. Now for simplicity, let me write capital D equals to D to the M. And all we know from the previous steps is that this small r should be bounded by capital R over D. Now here is what we get from the polynomial partitioning is that each piece is less than d to the minus 3 of the total BLP norm. So here, what I actually mean is that this function, this S lies in some cell in previous steps, and then we apply the polynomial partitioning for those cellular cases. So this might not seem to be a super strong estimate, but that's just enough. Then we also have this L2 bound. So maybe I will say, let's think that the previous step is cellular. So S lies inside a parent cell. Let's call it O. So S lies inside O. This hat means it's parent. And then, so all the A and B1 are actually estimate about its parent, but since it's lies inside or it's like kind of inherent, it kind of having the same property as its parent. For example, EFS tangential ELP norm will be smaller than its parent. Okay. And then we also have this geometric inequality. That is, the L2 norm is bounded by something times the approximation of the L infinity norm. This is because of the geometric lemma that we assumed without proof. That is, the support of this function is small because it's tangential to an adverse surface. So all the A, B1, and B2 are some iteration of the previous inequalities. And then when we put things together, so this is the step that we discuss using Cordoba or Tao's bilinear restriction. And then now we apply those L2 inequalities, and we get some mixed power of D and R. And in the end, we apply the B2 step to bound this quantity. So we have two estimates about this quantity. The L2 norm of Fs tangential. The first estimate is the geometric estimate about the support. And the second estimate is the estimate we can obtain from polynomial partitioning. So so even if we don't have control on the size of R, but when R is large, this estimate is better, so we can plug in. And when R is small, then this estimate is better, and we can plug in. After some algebra, I won't do it here. It's bounded by that. So I see if there is a question. Thank you, Harold. The Cordoba is on the first syllable.
Cordoba.
Cordoba. Thank you. Cordoba. Okay. And so this is Cordoba. Okay. I hope I've explained the main idea of Larry's proof of restriction estimate in R3, but there are some algebra that I didn't do, and also I assumed geometric lemma about the size of the support. And so that finishes the proof. I'll pause and see if there are any questions. Okay. Now we will discuss some ideas that goes on in Rn. So the rest will be like a talk. It will just give some intuition. We won't be able to see detail. So one idea is, like, before we discuss the broad narrow decomposition, we decompose the LP norm of F into a K broad part and a K narrow part. And those K narrow part will have Fourier support inside a lower dimensional version, a lower dimensional paraboloid. And one thing is, like, how do we control those narrow part? So here, since it is it is a program joined with analytic number theory. I feel like maybe I should discuss a little bit about decoupling. So decoupling is an estimate also about functions with Fourier transform supported on the paraboloid. So now we can, for any function g will be like EF. And then we can decompose g into sum of g theta. So g theta will be like EF theta. And instead of having just the triangle inequality, Pourquin and Demeter shows that when p is from 2 to this critical exponent 2 times n plus 1 over n minus 1, we have this little L2 decoupling inequality. The radius of theta is r to the minus a half, and then the ball that we are considering is BR. And this WBR is a weight function rapidly decaying of BR. So we have seen, as you might know, there are many applications of decoupling. So for example, in restriction theory, one application is how to estimate the narrow part, especially when K is like not 2. So now this is when we define the Broadband decomposition, we have we said something like, now the ball that we use have radius k square, and I said that at that time we should pay attention to this k square, and here is why. Because this ball has radius k square, and EF gamma A has Fourier support on the 1 over k neighborhood of a lower dimensional paraboloid. And now we can apply the Pourquin-Demeter decoupling. So since this is k square, so we can decompose into caps of radius k to the minus 1, and up to a loss of k to the epsilon. And now we have this little L2 inequality. But when so in the end, we want to sum over all the B in BR, EF gamma A, and also those gamma A's will change depending on B. So here is what we do. For a fixed B, we apply Hausdorff's inequality to pass from little L2 to little LP. And the loss here is like the number of tau inside, I think it is inside the gamma A. And we have some quantity here. And now once we have applied the Hausdorff's inequality, this sum tau, we can pretend that the taus will lie on all over the original paraboloid, and that's how we get rid of the dependence on the gamma A, the dependence of gamma A on B. So all we know is this is the gain that we have some quantity here, since that gamma A is like a low dimensional version, and then we can sum up. When I say it's a gain, it's like it's good when this little k, when we define the k-broad LP norm, is small, because this quantity is small. In particular, when little k is 2, this quantity is like 1. So it's super good. But when little k is large, we will lose more from decoupling. As we have just discussed, when little k is like n, well, we will lose a lot from decoupling, but we have sharp multilinear restriction estimate. So that's the balance between how we choose the k. When k is large, it's easier to prove good BLP k estimate. but we will lose from the narrow part. Okay, so this finished the discussion of the broad narrow and how the little k plays a role in high dimensions. And now, now let me just try to say something about how we estimate this BLP, this k-broad BLP norm using polynomial partitioning. So as before, we apply polynomial partitioning in Rn, and then we obtain a wall that's W is like R to the 1/2 neighborhood of an n-1 dimensional algebraic variety. In R3, so this n-1 dimensional algebraic variety is a two surface, and we kind of know restriction, how to do restriction estimate in R2. That's why we apply the Cordoba estimate. But in higher dimension, we don't know how to deal with the restriction estimate in Rn-1, where all we know is to apply polynomial partitioning again in Rn-1. And here is what we do. So we find a way to pretend that this surface looks like a plane in some sense, and then we do polynomial partitioning in Rn-1. So this reduction, I will just say it, is here we have, say, n-1 dimensional surface, a hypersurface. And then we can chop this surface into pieces such that each piece of this hypersurface will have tangent plane close to a hyperplane, like 1/100 close, not super close, but close, 1/100 close. And then if we, and then suppose that our piece of hypersurface is 1/100 close to a hyperplane, then we can apply projection to this hyperplane. And then we can do polynomial partitioning on this hyperplane and then pull back. This is what we do. Here we have a piece that's close to this, has tangent plane close to this hyperplane. And then we do projection and we apply polynomial partitioning on Rn-1, that is this hyperplane. And then we partition the quantity. The quantity is like, the previous quantity is this BLP norm, and then we can project the BLP norm to be a function on the n-1 dimensional plane, and we apply polynomial partition. And the cells downstairs will be a cell upstairs. And so we kind of have two types of iteration. One is within the same dimensional space, we keep polynomial partitioning until we arrive at a tangential case. And the second step is now we will need to apply a lower dimensional polynomial partitioning on the tangential case. And when do we stop? So here is when do we stop. We stop when the dimension of the variety is small k minus 1. This is by our small k broad, by our k broad assumption, and also the tangential tube assumption. Since on each cube, the set of tubes that's tangential to k minus 1 dimensional surface will lie in this neighborhood of its tangent plane. So this z, t, z, z. And when z it has dimension little k minus 1. So this guy will be a good candidate for the VA that we choose earlier. So by our definition of the K-broad norm, if F is tangential to a k minus 1 dimensional algebraic variety, then the K-broad norm is 0. Because we can kill everything by the neighborhood of the tangent plane at every point. So this is where we stop. And then on the last page, I will discuss one additional idea that we need in polynomial partitioning in restriction theory in higher dimension. That is the transverse equodistribution property. So this transverse equodistribution property is a fancy way of uncertainty principle. So we will need it when we try to combine estimate that's tangential to different scales. So for example, if our function here is tangential to an m-dimensional algebraic variety, let's, for simplicity, just view this algebraic variety as an m-plane. And it's tangential to, at this scale, that is R1. So, and every time when the radius becomes smaller, we will need to redo wave packet decomposition. And so we are dealing with some smaller wave packets. And now we continue partitioning this M plane. And we partition and partition until we have obtained the tangential case inside this M plane. So a function now is tangential to this, let's say Z1, that is the M plane, and also tangential to Z2, that is M-1 plane. So a function, so this is our new S. And all I want to say is that since it's tangential to the Z1 at a fairly large scale, on the frequency side, the support on this direction is very small. So this is Fs, support of Fs. Now, if we work out the uncertainty principle, it's in heuristic, it says that the EFS should be locally constant on this direction. On the normal direction of the Z1 plane. And so this is because the Fourier support is smaller. And then by uncertainty principle, then it's locally constant on a fat thing. And that's how we put the information of tangential cases in different steps together. So we have this extra locally constant that this will help us gain something when we put all the information together. Yeah, that finished all the lecture. Thank you very much for your attention.